Last step in the last component in an EEG system is the data recording and analysis component. Most commercial systems, both EEGi and NeuroScan that we have in my lab, they have separate software tools for recording and analysis, so it'll all be one package. In NeuroScan, it's called Scan. You record the data, and then after you record the data, you open you open the edit version or the analysis version, and it'll pull up your recorded data. Couple of important things. Usually, if you want your recording software to incorporate markers that are coming in from your stimulus system, and by this we mean time markers, you have to set that. It's a setting in the software, and it's very, very important that you do that. If you don't know when your stimulus was presented, there's no way you can analyze the response and know that the response was consistent with when the stimulus was presented. So it's very important to know that. It's very important to have a common t=0 starting point. And so usually the software does that, but it often doesn't do it automatically. There are homemade systems that use MATLAB and LabVIEW or both. The problem with a lot of analysis software is that there are two problems. One is it's fairly limited in capabilities. So you may get some very basic power density maps. You may be able, a lot of systems now do, they actually do some coherence and connectivity. Some systems even do wavelet analysis, but it's their analysis. And the other problem is that unless you have forked over the additional 10 or 20K for the software development kit with many of these systems, then you don't really have access to how their algorithm is written and what it's actually doing. So it's somewhat of a black box when you run a lot of these external companies' system software, and a lot of us in engineering don't care for that. We want to know exactly what our algorithm's doing. Fortunately, there's some third-party software. You don't have to do all your own coding in MATLAB because there are a number of third-party software programs. The most popular one is EEGlab, and the reason it's popular is that it's free and it's pretty good. It's widely supported by a huge community of people who develop toolboxes for EEGlab, and so and in fact they have really a full open source with lots and lots of documentation and lots of user contributed toolboxes and add-ons. So in this class, we will use primarily EEGlab along with some basic MATLAB code that you write. But there are some others, and some of them are quite expensive. And some of them, the more expensive they are, the more black boxy they are, and the less you're actually able to see. Okay, well, let's talk a little bit about the EEG cap or net. And so in talking about that, first we want to define what is an EEG montage. So an EEG montage refers to how the probes are laid out on the scalp and how they are connected electrically. So the kind of classic system is the 1020 or 1010 system. If you find the recession right at your nose, and you find the little piece of bone right at the base of the back of your head, and you call that distance 100%, then you can divide that into 10%, 20%, 20%, 20%, 20%, and 10% intervals. That's why it's called the 1020 system. And the electrodes are laid out then on a grid. And so many of the caps, the conventional caps that you buy, will have this kind of layout. The EEGi system in my lab uses a different kind of system. It uses a geodesic layout. It does that because the goal is to equalize the stress on each electrode so that they hold each other in place, and then that force that's holding the net in place First of all, it minimizes any localized areas of force that might cause pain or discomfort. And secondly, it tends to have an equalizing effect on the impedance between the probe and the scalp, since these tend to be high impedance systems and work off of a solution as opposed to a gel. Then that's important. So those are the two common kinds of caps. The montage refers to how the electrodes are referenced. Remember that any voltage measurement is always a differential measurement. You can't measure the voltage of a point. You're always measuring the voltage between a point and something that we often call ground. In EEG, that's referred to as the reference, and how you reference your EEG and how you lay out your probes are related. So a referential montage is where each electrode's referenced to a common electrode. Usually that's either an electrode in the center of the head, or you actually have two references, one for the right side on the right earlobe and one for the left side on the left earlobe. A bipolar montage is where each electrode is referenced to an adjacent electrode, and there are a couple of ways to do that. So let's look at some pictures. Here are two types of bipolar montages. So here on the left is what's referred to as the double banana for obvious reasons. Here, if you look at this electrode location, what's actually going into the amplifier is the differential measurement between this electrode and this electrode, and between this electrode and this electrode. So you're not measuring the potential between this electrode, which is FP1, and some reference point. You're measuring the difference between FP1 and F7. So a channel then is this difference. This is the most commonly used bipolar montage. The transverse montage is another montage that runs from left to right across the head. Not as commonly used, sometimes used when people are looking at epilepsy and trying to get localization across hemisphere. So those are the two bipolar montages.